circuits is probably one of the most difficult ones I've seen, especially from part B onwards, so I thought it'd be good to have a look at this. Part A is relatively okay, so it's giving you two lamps X and Y. For X, it's giving you the voltage, the power through the lamp, and it's asking you to find the current. So we can do that because yeah, just a reminder, your approach to this question should also always be look for any equations that you can use to substitute into if it's easy enough for that question. But if that doesn't work, then use what you know about current and voltage in series and parallel. But the equation linking power, current, and voltage is P equals IV. You want to find current, so that's power divided by voltage. In this case, that's 36 divided by 12, so that's 3 amps. Because we're also given the power and voltage across Y, we can find the current using the same formula. In this case, it's power of 2 divided by voltage of 4.5, which will give you 0.44 amps to 2 decimal places. So now what we have is an EMF of 24 volts. It's also told you that these, by the way, lamps X and Y, they're from the previous question. So let's label the voltage of each from the previous question as well as the current because it will be useful. So 0.44 amps, and this one is 3 amps. Now it's asking for the PD across R1 to start with. I'm just going to rewrite these out. Okay, so the potential difference across R1. Can we use any equation? Well, do we know the current across R1? We don't yet know it, and we also don't know the resistance across it, so we can't really use any equations. So let's use what we know about current and voltage in series and parallel. Now this resistor on the left is in series with this whole junction on the right. Why that's important is it means that, well, in series the voltage is split up. So the total voltage of 24 volts is split up across here and this whole junction here. If we find out the total voltage that goes into this junction on the right, we can take it away from 24 and that will be the voltage that goes through R1. So let's focus on doing that. Well, through the bottom there's 12 volts, we know that already. And we also know that in parallel the voltage is the same, meaning that in the whole top of the junction there's also going to be 12 volts. So let's write that down. Why that's important is, sorry, I'm just going to rub it out just because I don't want the diagram to get too messy. But what it means is that 12 volts goes into this junction, and because we know that in parallel it stays the same, it's the 12 volts isn't split up. There's just 12 volts that go through the bottom and 12 volts that go through the top. But if 12 volts is taken up by this junction on the right, that means that this junction must take up 12 volts also. So R1 has a voltage of 12 volts flowing through it. Now the current through R1, once again, if we have the potential difference now, but if we have one more component like power through R1 or resistance through R1, we can just use one of the equations, but we can't do that. Instead, we use the fact again that this resistor is in series with this whole junction. So if we find the total current flowing through this junction, that will give you the total current also flowing through R1, because in series current is the same. Okay, just again gonna rub this out because the diagram's getting a little too messy. Okay, so the current through Y is given as 0.44 amps. These two components are in series. In series, we know the current is the same. So the current through here would also be 0.44 amps. but how much current goes into this junction? This is what confuses students. Both of these, what students tend to do is add the currents together, but we don't do that because we know that in series current is the same. So if 0.44 amps flows through the whole top of the junction, that 0.44 amps is the same across both components, meaning that 3 amps will flow through the bottom because that's the current across X, and 0.44 amps will flow through the whole top of the junction. So the total current going into the junction is 3.44 amps. Because, like I mentioned, R1 is in series with this whole junction. In series, the current will be the same, so this will also have 3.44 amps. That was the most difficult part of this question. You have to really be careful about dealing with current and voltage in series and parallel. But yeah, main thing to remember, even though both of these components have 0.44 amps, the total current flowing through the top of the junction is still 0.44. It's just not being split up because they're in series, so current isn't split up. But the total current going into the junction is being split up because, well, it's parallel. Now the PD across R2. Well, we mentioned the current. Actually, we don't even need to use that because we know that, let me use a highlighter here. The voltage in parallel is the same. This X is in parallel with this whole combination here, meaning the whole combination here will also have a voltage of 12 volts. So we do 12 take away 4.5, and that will get you the voltage flowing through R2. Now 12 take away 4.5 is 7.5. If you do need to rewatch any point, please feel free to, because I remember myself when I did A-level physics, it took me like a good 15 to 20 minutes, maybe even 30, just understanding what was going on in this question, even after getting the right answers. Calculate the resistance of R2. Where is R2? It's just here. Now that we know the current across it and we know the voltage across R2, we can just use R equals V over I. You can use 0.44, but I'm going to use 2 over 4.5 just to get a more accurate answer. I'll give you 16.9. Okay. Hopefully that made sense. Like I mentioned, this is probably the most difficult question on electricity. I'm going to rub all this out for part C, just because everything's getting too messy. But if you do need to, you can just always rewind the video and go back to finding the values. Okay. This is where most marks are actually lost in the questions, actually, with electricity. So let's go through this. So the filament in X breaks. The lamp no longer conducts. It's observed the voltmeter reading decreases. So the voltage across R1 decreases. And lamp Y grows more brightly. Current, by the way, relates to brightness, meaning that if it's brighter, there's more current flowing through. Without calculation, why the voltmeter reading decreases? Let's think about it like this. Before, this whole thing was a parallel combination, and in parallel, the total resistance is smaller. But now that X has been broken, like it mentions in this question, this is now a series junction. So in series, the total resistance is larger. Why that's important is it means that this combo here now has a larger resistance, meaning because of what we know about voltage being proportional to resistance, more of the 24 volts will be taken up by this junction. Taken up by junction on right. just a reminder that this junction on the right is in series with this one on the left. So if this now takes up more of the 24 volts, that will leave a lower proportion of the 24 volts flowing through R1. So that's the answer to that. Sorry for my handwriting, by the way. I'm just getting used to this new writing pad of the EMF, or 24 volts now flows through R1. One last part to this question, which is explain why lamp white grows more brightly. Well, that's because before the current that flowed into this junction, it was split up because it was in parallel. But now that it's a series circuit, the current isn't split up anymore. So you mentioned that it's now a series circuit. That'll be your first mark. My handwriting's awful, sorry. And then we say the current is no longer split up. And please feel free to rewind, and if you have any questions, just let me know in the comments, because that was very difficult. But thanks for watching, and have a good rest of your day.